Well, good afternoon, everybody, and welcome to the latest in this series of webinars from the Ground Source Heat Pump Association. Today, we are hearing from Hugh Williams. Hugh is a highly experienced hydrogeologist with lots of multinational experience in the modelling of groundwater, and Hugh is here today to talk to us about numerical modelling of open loop ground source heat pump systems. We will be continuing on the open loop theme over the next few weeks, but let's hand over to Hugh now and hear all about his modelling experience.
Okay, thanks, John, and thanks GSHPA for inviting me to speak as part of the 2020 seminar series. I've tuned into a few of these live and on YouTube, and I think the standard of presentations and the volume of information disseminated has been monumental. So really, thanks to all involved in presenting and organising. It's no mean feat, and thanks for tuning in today on this second talk on open loop systems. Hopefully I won't be too data heavy or on quite a dry subject, and it'll be more of a stroll through the subject. So that we're all on the same page, I thought I'd better just start with a gentle reminder of what a hydrogeologist looks like. We're not all in the same room, so this is a rhetorical question, unfortunately, but photo A, that's a picture of me, an excuse to put me in a far-flung project, as John says. That's me in the Atacama Desert in photo A. Photo C is Charles Tice. He's a hydrogeologist who resolved some of the issues around groundwater flow to a well. Henri Darcy is a Frenchman who empirically resolved some of the questions about how water flows through porous media when he was researching how to get clean water to the fountains of Dijon in his native France. Photo F, that's worthy of mention because that's a hydrologist, someone that's interested in surface water flow and occurrence. But I'm a hydrogeologist and I'm concerned with groundwater flow and occurrence, and therefore groundwater open loop systems. And then photo B and E, they're both actors in some way or another. So now that we know what a hydrogeologist looks like, we're just going to confirm what these open loop ground source heat pump systems look like. The above ground part, the part outside of the grey dotted area there, that's going to be Chris's domain for the final presentation. But for clarification's sake, I'm looking at the bit inside the red box. So the abstraction of groundwater, normally from a borehole, passing that through the heat exchange and then getting that back into the environment in some way. It's probably worth noting that returning water back to the aquifer isn't an operational requirement of an open loop ground source heat pump system. More, it's a regulatory or best practice approach to open loop systems. The key being that an open loop system that abstracts water from the environment and returns it to the environment from where you got it is resource neutral. So we're not consuming any of the water resource at the site or in that catchment. So briefly then, in a little bit more detail, what sort of systems do we typically model with our numerical models? Well, we have a unidirectional system where we have a dedicated abstraction borehole, dedicated injection borehole. You could call that a bit like a pump and dump system. Of course, when flow rates and thermal loads are required, we have multiple boreholes, multiple abstraction boreholes, multiple injection boreholes to increase the flow rate past the plates. We could have a reversible system, probably less common, but this is one where each borehole can be an abstraction and injection borehole. Often these reversible systems are used in aquathermal energy storage, ATES systems. And finally, and this one's becoming increasingly popular recently, we've got one where the open loop system is couples groundwater to surface water, either a lake, river, or the ocean. As I say, this is becoming increasingly popular, and that poses some really interesting issues for us as modelers, how to assess that. One that is also becoming increasingly popular that I'll not touch on today is the use of mined water in abandoned mine workings. David Banks will be covering this topic next week in a much more I'm sure in a much more detailed manner, but suffice to say, for the purposes of this presentation, many of the numerical modeling approaches are the same. Certainly the software that we can apply to these sorts of systems would apply to many of the mine water applications. Another thing that I'll not touch on just yet is the purposes, the purpose for modeling. We're going to assume that we already know we need a groundwater model. I'm not going to go through the decision-making process and why there are other and often more applicable alternatives. But as Chris mentioned in his opening presentation, not all open loop ground source heat pump systems require numerical modeling, and also not all ground source heat pump projects are located above suitably yielding aquifers. Okay, so what does the groundwater model look like? Well, we start any groundwater modeling project with a conceptual model of the site. At best, this is a well-characterized understanding of the controlling factors that influence the behavior of groundwater flow and heat transport in the subsurface. We construct this conceptual model typically using experience of similar geological settings and systems. Of course, we use published geological mapping, borehole records. We've touched on this in other presentations, any other relevant site reports. All these factors are considered by the modeler and used to formulate the conceptual model. This is the conceptual model that they hold in their head. At the other end of the spectrum, we have a worst case scenario where the conceptual model is purely a figment of the modeler's imagination. We hope we don't have that too much. We then have to squeeze our imagination into the modeling software. We get what we imagine onto the computer. So our numerical model is an approximation of the site. It's applied into a three-dimensional grid consisting of layers and elements within the model that have specified hydraulic and thermal characteristics. And these models extend out in a 3D domain to a depth and area that the modeler or the regulator deems appropriate to assess what we're looking at. These numerical models, they incorporate the boreholes, they rivers, recharge, thermal heat fluxes, and all sorts of bells and whistles that the modeler has to give regard to including or leaving out, which is equally important, depending on the conceptual model they have in their head. We run through various modeling processes, calibration modeling, uncertainty analysis, to give us an understanding of the site that may or may not be better than predicting the future as reading the entrails of a disemboweled chicken, until we get something like predictive modeling that gives us an answer or the results. Unfortunately, anyone involved in predictive modeling will let you know that it's hopefully not as simple as that, and we do have some problems. One of the slight problems, we're not going to focus too much on some of the maths of the problems, but it is something that our friend here, Gaza, can shed some light on. Reported as replying once to a question of which particular team will win a football game, Gaza replied, "I don't make predictions and never will," which is quite a good mantra for a groundwater modeler. One of our issues is there's no reason why a numerical model should be able to accurately predict the future. One of our problems being that a model cannot tell us what will happen in the future. It can actually only really tell us what won't happen. And the range of predictions that lie within the not possible bounds may be quite large. So at the very best, a modeler can reasonably justify something along the lines of, I'm not going to give you the right answer, but here is a model whose potential for wrongness has been minimized, which is probably not what Jimmy Hill and the guys at Match of the Day were expecting to hear at the time from Paul Gascoigne. So that leaves us somewhere on the modeling spectrum, the groundwater modeling spectrum, which I've pictorially represented here. A model that we know is wrong. This is our model, but we have tried to make as least wrong as possible. Now, is that a bad thing? Heck no. No, I think we all understand that a model is a defective simulator of the real world. We intuitively know this to be a compromise, but it's worth reiterating and it's worth agreeing that that's okay. It's okay because it's still the best tool we have to support our decision making, so long as we don't sweep this compromise under the rug. And what is the purpose of any model? Well, it should help us make decisions to avoid a bad thing happening. There's always something bad on the horizon of any project, be it failure to achieve flow rates, getting unacceptable hydraulic or thermal interference. In other words, anything that can adversely impact the sustainability of the open loop ground source heat pump system. Models can and do help us understand, good models can and do help us understand the statistical gap between our bad thing happening and our model predictions to help us manage risk. So what are some of the main risk factors that potentially adversely impact the sustainability of an open loop system? Well, I've tabled a few of them here. These aren't all of them, but these are certainly some of them. Obviously, we have the thermal and hydraulic impacts. We've got the thermal and hydraulic impacts happening on site or off site, and who that's of interest to. We'll take a quick stroll through these in turn. Thermal interference, well, as much as I would like thermal interference to be Hillary Clinton photobombing this ground loop system here, I think hopefully you can see on your screen well loop supply and well loop return. That's not thermal interference, I'm afraid. Thermal interference is when the colder or warmer water that we put back into the environment makes its way back to our abstraction point. So what can models tell us about this thermal interference? Well, from the thermal interference from an on-site perspective is shown here in some of these modeling outcomes. This is a system in London. We've got the heating and cooling load over a year. You might be able to see this is each week of the year, and this is each hour of the day. So you can see that in January, at the start of the year, we've got some small heating load in the morning to warm the building up, and then by the time we get to May, we've got a predominantly cooling load that's strongest in July, August, and June, and then recedes back to December with some heating load. So these are the loads that we convert into flow rates and delta T's for the groundwater model, and our prediction here. You don't have to read the you don't have to be able to read the axes on this graph. Suffice to say that this is a 35-year prediction of the abstraction and injection temperatures of a 4-borehole open loop system, and you can see this annual fluctuation, this annual cycle of heating and cooling dominant playing out every year in the abstraction and injection temperatures. And you can see that it takes, well, 1, 2, 3, 4, 5, about 15 years or so before these abstraction and injection temperatures on this cooling dominant system start to reach dynamic equilibrium with the aquifer. We certainly don't achieve that in the first 5 years. We can still see that temperatures are still changing. So to gain an understanding of what happens in the future, we need to do this sort of predictive modeling. There's no way to say that the fate of the groundwater, the thermal energy in that groundwater is going to be without investigating these sorts of issues. And on the other side of that, we've got 3 cross sections cut through a 3D model of an aquathermal energy storage. We've got the boreholes modeled in the model as little flags, like little golf flags, and you can see that over time, these 3 different screenshots, we've got thermal energy, a bubble of warmer water being stored in the ground, got that moving away from the borehole and then being drawn back according to the interseasonal storage that this aquathermal energy system is trying to predict the behavior of. It's the sort of thing that is very difficult to conceptualize because it has so many variables. We find it very difficult to predict something complex like that without the use of a model. The other thing that the model can give an indication of is the abstraction and injection groundwater levels and temp pressures. Not normally as dramatic as something like we can see here where we're flooding a plant room. And to be honest with you, if you're using a model to predict this, you've probably had the wheels fallen off your system already. It's just included here for completeness. The other side of the impacts that we try to elucidate with our models, the thermal impact on the aquifer. So what happens off your site? Well, we've got an example here that I worked on earlier in the year, a 4-borehole system dedicated in pairs, 2 abstraction wells, 2 injection boreholes, and you can maybe be able to just see them on the map view here. the thermal impact is the fate of the warmer water in this cooling dominant system as it flows down gradient through the aquifer. You can see that again in cutaway view there. The boreholes are the little flags, and you can see that over the 35-year run of this model, we have this thermal plume moving down hydraulic gradient in the aquifer towards these other abstractors. Now, given that this is a screenshot when the system has reached a sort of a thermodynamic equilibrium with the aquifer, so this plume then ceases to expand. And by that I mean that the amount of thermal energy that we're putting into the ground via these injection boreholes has reached such a size of plume that the thermal exchange is no longer expanding. And this is 3 screenshots, not through time, but this is 3 slices through the model at the same time. And you can see how the thermal plume has developed with depth of the injection. So this is a London example, and in this case we could quite safely say that the down gradient abstraction was not going to be adversely impacted by the operation of our system. I guess the other item of interest to off-site groundwater levels, particularly from the regulator, is what is the impact of our lowering groundwater and raising groundwater around our abstraction and injection wells. Again, going back to a case in London, we have the Environment Agency that likes to impose a target range of groundwater levels such that groundwater remains above the top surface of the chalk aquifer. Despite our systems being resource neutral, the Environment Agency still like to apply set targets for groundwater levels. So our model hopefully demonstrates the prediction that our system stays within this range of target groundwater levels through time. Which brings me quickly to another view of the groundwater model, and let's see if this works. Oh, there we go. So this is the modeling software that I use. It's called FIFO. It's published by a German company called DHI Vossi. It's certainly an industry standard for coupled groundwater flow and heat transport modeling. And what we can see here is the predicted impact of a 2 borehole ground source open loop system. We have the injection borehole, which is down gradient of the abstraction borehole. We can see the impact of a cooling dominant system. So we're dumping warmer water into the aquifer. This is moving away from our pump and dump system. And it forms this plume, as we've seen in some of the other slides earlier. And this is a evolution of the plume over time. And you may be able just to see that the abstraction borehole is drawing this warmer plume back up towards it, and this is what we mean by the thermal interference between the abstraction and injection. But this is actually just a purely theoretical case, but we can see that the down gradient abstractor here potentially would be impacted within the duration of the model prediction over time. So if this is a temperature sensitive receptor, say this is an existing ground source heat pump system, most notably, we would say that we'd have the potential to adversely impact that borehole, which is obviously something that we don't want to do. This is the same theoretical site in London, just the model again. Nope, that's the same one. Let's try this one. That looks different. Same system. You can see that the groundwater model is replicating the flow through the aquifer, this time in cross section. And it's interesting to perhaps note that this is the top of the aquifer, this is the bottom of the aquifer. We've got most of the thermal transport going along within the bounds of the aquifer, very little vertical propagation of the thermal plume. It certainly predominantly moves with groundwater flow and moves within the bounds of the aquifer. So I guess the question when to model It's a good question. It's asked by others working in other industries that interact with groundwater modelers, the water resource industry, the mining industry, infrastructure, contaminated land. It's a good question. It's a good question because groundwater models cost money. No industry has defined a specific set of criteria which answers this question: when to model and when not to model. And I'm afraid the ground source heat pump industry is no different. And obviously, based on this slide, you're going to predict that I could say that my opinion is that it's a risk-based approach. Anyone working with risk will know that it's defined as the chance of something happening against the severity of its outcome or severity of cost to put it right. And a groundwater model should assist with us de-risking a project. So the risk is obviously strongly client influenced, and also, of course, it's site influenced. Do we need an expensive numerical model on a small open loop system that has well-balanced thermal loads, heating and cooling about the same, in a major aquifer that's very remote to any potentially temperature sensitive receptor? Well, no, probably not, because the risk there is small. It's down here in the bottom left-hand corner. Low likelihood of and low impact. Do we need a model if a project is large, it exceeds some thermal threshold or flow rate? Well, as I said, there is no threshold, but there is certainly a correlation between bigger, more expensive projects in areas with more temperature sensitive receptors, such as lots of other ground source heat pump systems, or even an environmental receptor such as a spring or a wetland that the Environment Agency or the local regulator may have a concern over. Let's say this wetland receiving warmer or colder water from the operation of your ground source heat pump system. Well, that will be the sort of project where we would tend to want to de-risk or at least investigate the chance of that adverse impact happening. There is no tipping point about when a groundwater model should be applied or shouldn't, but there is certainly a correlation between the size of the project and the density of other receptors, other temperature sensitive receptors. So perhaps we have risk averse clients may still want a groundwater model, and perhaps we have risk taking clients that may not feel the expense of a model is worthwhile. So to wrap up, perhaps the question's always asked of modelers, groundwater models: what's the minimum distance between boreholes? Well, how big is the site? How much flow is required of the system? What's the thermal balance? What's the groundwater flow mechanism? What's the groundwater through flow or the regional gradient? Are there any temperature sensitive features in the vicinity of the site? The answer to what's the minimum distance between boreholes? Well, better ask an experienced open loop designer. I think this hopefully rings to what Chris was saying in last week's talk. I guess the other question that we already answered as well: when do we need a groundwater model? Well, same set of questions and the same silly answer, I'm afraid. Ask a experienced open loop designer. Same question, same dodgy answer. But believe me, we don't always say yes. There are alternatives that we often apply. We don't need a big numerical model always. There are often more suitable alternatives that may well satisfy the risk profile of the project, that may well satisfy the regulator, and certainly we don't always say yes. So that's brought me neatly under half an hour, and thanks for listening. John, I don't know if you're still awake. Yes, they were, and have any questions?
Well, thank you very much, Hugh. Fascinating stuff and beautifully presented. It's a huge subject area, open loop, and modelling of them is just one of them. Yeah, that was very nicely done. Thank you very much. Yes, we do have a few questions coming in, and I've certainly got a couple myself. The first question is from Duncan Ray. He would just like to know approximately what the distance was between the injection and abstraction boreholes in that model playback that you showed to us.
Oh, that being a theoretical site, I think I just assumed it was a fairly typical London block, an office block in London. So I think I had about 50 meters in that case. But as I said, the little movies were actually shown to have a nice big. I rigged the model to have a nice big plume, so the groundwater through flow was quite strong. Typically, we might see a bit more recycling of injected water than that. Probably the screenshots that were just the photos from the model, probably a bit more representative, where we have the thermal plume moving more up gradient towards the abstraction boreholes. But in fact, in those pictures as well, the separation there was about 50 meters as well.
Okay, and from Ian Howley, Hugh, do you agree that it should be borne in mind that whilst modelling may not be deemed necessary on sites with plenty of space, they can be useful to help reduce civil works associated with the unnecessary spacing of boreholes?
Yeah, absolutely. And I think it comes down to one of these questions of of cost benefit. Even when we're not trying to de-risk a project, the opportunity to tighten up our design, if that exceed, obviously if the cost of the modeling is less than that which we can apply to tightening up the design, then absolutely. And it's not just, as I said, I only, this is a quick run through the highlights, but that's a really good point, Ian, that we hope that our model can optimize the operation of the ground source heat pump system as well. Perhaps we can have higher flow rates, change the delta T's. We can operate, especially when we've got multiple borehole systems, so more than one abstraction, more than one injection borehole. How we abstract from those and inject on those may not be just an even split between them. It may well be that we can optimize the operation, reduce pumping costs, reduce spacing, as you said, all sorts of things. We can run scenarios in the model before we put the boreholes in, before we go to the expense of drilling, before we go to the expense of piping them up and equipping them. We can run scenarios in the model such that we can test these different operational setups. So yeah, no, that's a really good point, Ian. Thanks for bringing that one up.
Okay, so, and Chris asks what he knows is an impossible question, but what is the typical cost of a model for, say, a 2 borehole open loop project in the middle of London?
Well, yeah, probably over the years I've been involved in a few of these London projects. So in some ways, the price is coming down. The London of the geology of the London basin can be quite repeatable. So going back to the modeling process, we have this conceptual model, and the conceptual model for a London site, we have quite clearly in our heads. We've got great mapping, and we've got the number of boreholes that Chris, you put up on your presentation. There are many boreholes in London over the years. We can get a really good understanding of the site conceptually. We already probably have a fairly good idea of what the operation of the system might look like, because obviously with groundwater modeling, we don't like to give the answer, because as I've said, we can't. We more like to demonstrate our understanding to be accurate. So long answer is probably a short question. Because we have a great idea of the site, in London we might be around £5,000 to run the various scenarios and produce the modelling report. And I would add that one modelling report would be suitable to provide to the Environment Agency for their environmental impact assessment criteria, and that same model and that same report can be used as a design. Going back to Ian's question, design and optimization, the one model can have those two purposes. It can advise on both. At the other end of the spectrum, if we've got a large site in an unusual aquifer, the cost, it can go up significantly if we have a more complex system in a more unusual setting.
Okay, and a question from me. Would you say the type of modelling that you've shown us here is equally applicable to all of the aquifer types that are used for open loop in the UK?
Yeah, absolutely. The flexibility of the software, as I said, it's actually a German software. It was first released in 1979, and it's been developed ever since. It is capable of any 3D configuration that we can imagine, and it is capable of inputting any hydraulic and thermal characteristics that we can imagine. So the only constraint is that we have to import our understanding of the site into the model, typically as layers, but nowadays we have unstructured grids, and we can do all sorts of clever things. We can directly import 3D geological models into the FIFO software. It's a software that isn't particular to the ground source heat pump industry. It's a modeling software that's been used extensively in mining industry infrastructure. It's exactly the same code. It's used for all sorts of applications. I've personally used it a lot in Australia on mining projects, tunneling projects, anything that has groundwater flow through porous media. It can also replicate fracture flow. It's an incredibly robust, very expensive piece of software that has many applications. So we can definitely apply that to any subsurface application.
Okay, and a question from Peter McConvey. For a new scheme for areas where other open loop schemes are operating, do you model the heat and cool effects from each system on the aquifer to see the interface effects?
Yep, no, that's a really good question. And certainly that's something that's becoming increasingly important, particularly the multiple projects that are going on in urban areas nowadays. We do. I didn't touch on much of the modeling process, other than to say quickly that we create an initial conditions, we calibrate that model, and then we do predictive runs. But part of the let's split it up into two answers then. The regulator would require typically a cumulative impact as part of the environmental impact assessment, and in that we would import into the model the licensed use of each groundwater license in the vicinity of our site that lie within the model domain. So when doing a model in England, we would request the license data from the Environment Agency. That can take some time, but that's okay because so does modeling. So we get the actual abstraction, the licensed abstraction rates at least from all the local boreholes, and we actually import those licensed abstraction rates into the model. We know that what their purpose is, whether it's heating and cooling, because not all information on licenses is publicly available. We can't have their actual use. We can only have their license use. We do have to make some assumptions around their operation, but typically what we would do, because this is for cumulative impact, we assume that the local licenses are operating at full licensed capacity. We can then see the impact that adding our system has to the existing groundwater landscape, as it were, what that cumulative impact is, and if we impact others. So in that example of the movie where we had the plume heading down hydraulic gradient, the reason it was drawn towards that other borehole was because we had the abstraction details of that borehole, and we knew how much that was pulling out and what effect that had on the shape, length, and size of the thermal plume. So absolutely, the regulator would require that cumulative impact. And then going on to the operator, answering that for the designer and operator of the system, we obviously want to know whether the system adversely impacts others, because there's a right to claim back derogation issues if your system impacts another. And if there's someone upgrading of you as well, you want to know before you put your borehole in, are you going to be already abstracting much warmer water because someone's got a cooling dominant system next door to you? So absolutely, that's all part of what we can model, and what we should be modeling.
Okay, and a question from Tom Pine. Be an expensive question for you. Tom is asking, all right, so how much approximately does FIFO cost, the modeling software?
To buy, last time I asked, which was a few years ago now, if you wanted to buy the software outright to get a permanent license with support, I believe it was if memory serves correct, I believe it was 34,000 euros to buy outright. Now, there are ways in which to hire the license. Personally, what I do is the company DHI obviously have a cloud computing option now. So I log on to AWS, Amazon Web Services, through the portal, through the license I bought through DHI, and I actually rent a great big modeling machine somewhere in the world. And that's a really cost-effective option because I don't have to buy an expensive numerical modeling computer. I can go onto one that's an Amazon Web Services one. I pay an hourly rate for an annual fee, and that's a much more cost-effective way to access the software. I would add to that there's also a viewer that you can download for free, and you can view others' results, but you can't run models on that. But yeah, because it's a software that has so many applications. It's got a lot of bells and whistles. We don't use them all for numerical modeling of open loop systems, so it's a big old complex model.
Yep, and a couple of people pointed out that you can't just buy the software; you also have to know how to use it.
Yes.
It takes an awful lot of experience and skill to do so. And I think we will wrap up with one final question. If you've got a comment on this, Hugh, for small heat pumps, what's your view on using one borehole with a hydraulic plug halfway down and discharge below?
Yeah, well, my comment on that would be ask an expert. They are used in North America. A standing column, that would be without the hydraulic packer or the plug in the middle. If the aquifer, it's the aquifer that has to dictate the opportunity to do that. There are certain circumstances where that would not work, well, when I say it wouldn't work, it wouldn't work above a certain flow rate. But there are certainly, with careful investigation, with careful modeling, this sort of system has been demonstrated to work very nicely. And I think probably Ian and Andy Howley could probably both comment on that, on the success of the operation of that. And I know that they're the guy that they team with modeled that extensively, and I think that they're getting some really good results out of that. So certainly it's a really interesting option, and the configuration of boreholes, abstraction and injection are limited by your imagination given the site characteristics. There are other sites that obviously, like as I said, don't have these packers, the standing column wells. They're popular in North America, and you might read that they only work in fractured aquifers, but yeah, the modeling software can certainly give us an indication of how that might work, but there's a lot on the ground to do with a setup like that. It's certainly not modeling. Modeling might help with the prediction of it, but yeah, it's definitely a great option where space is limited.
Okay, well, I think we'll probably be able to leave it there. But yeah, Chris Davidson makes the point that single hole open loop systems, standing column wells might be the subject of a future session. So many thanks again, Hugh. That was a fascinating webinar. We all appreciate the amount of work that people put in to be able to present these webinars for the association. Everybody, please do remember that all of these webinars are recorded and they are available as a webinar and the slides on the GSHPA website. And also remember, next week we continue with the open loop theme, but a bit different. It's Dave Banks. Dave is always worth a good listening to. And Dave is talking about mine water open loop systems. So Dave will be on at 1 o'clock next Thursday, and we hope to see you all then. So I think that's probably it for now. Thank you very much for attending. And that's it from the association for this week. Thank you.
Thanks all. Thanks, John.